We've talked about definitions for probability, including things like an experiment, a sample space, an event, and a probability. The probability that we defined was a theoretical probability in which all of the outcomes are equally likely to occur. There's also something called an empirical probability, and that is a probability based upon observation rather than just like the theory of if you flip a coin, it's 50% heads, 50% tails, or equally likely heads, tails. Or if I draw a card out of a deck, it's 1 out of 52 times it's going to be a king of hearts or something like that. And so instead of the theoretical probability, actually looking at data and seeing if it matches up, that's the empirical probability, okay? So the theoretical probability, obviously, that's the number of outcomes in the event divided by the total number of possible outcomes. And I talked about that before in a previous video. That's the cardinality of the event divided by the cardinality of the sample space, right? If you think about those as sets. Well, the empirical probability is if you were actually to perform the experiment, how many times did you observe the event versus how many total times did you run the experiment? Okay, how many observed occurrences? And so that ratio gives you the empirical probability. All right, so let me give you an example. I'll actually run this through using a deck of cards. And so here I have cutting a deck of cards. So that's just like you have your deck, you cut it somewhere and look at the card, look at the face card, right? Or whatever's there. So cut a deck of cards. The sample space size is 52. Cardinality of the sample space 52 because there are 52 cards in the deck, assuming I have a full deck here, which I didn't count them, but I assume there is. And I want the event, the cutting of a spade, okay? So that's this guy right here. Now, the theoretical probability can be easily calculated. I don't have to run the experiment. I just know that in that event, there are, the cardinality of that event is 13 because there are 13 possible spades in the deck, right? The numbers 2 through 10, and then the jack, queen, king, and ace, and make 13 total cards. I also know that the cardinality, I already have that. The cardinality of the sample space, the whole deck, is 52. And so my theoretical probability, if I were to calculate that, I'll put that in green to be consistent here. Theoretical probability is just the 13 n of e, cardinality of e, over 52, which ends up reducing down to 1/4, okay? Or, you could divide the top and bottom by 13 to reduce that fraction to a quarter. You could say 0.25 is a probability. A lot of times we represent probabilities as decimals, or 25% as a percentage, okay? So 3 different equivalent forms for that probability, but I'll just keep it as a fraction of 1/4. So what I'm going to do, that's the theoretical probability. Now the empirical probability is actually taking a deck of cards and seeing if it works, which it should, or at least be close. And so in theory, the more times I cut the deck, the closer the empirical probability will be to the theoretical probability. In theory, we'll see if that works. So what I want to do is I'm going to run this, let's say I start, run it 4 times and 8 times, maybe 20 times, I don't know. We'll just cut the deck and mark down what suited the card is, okay? It's that simple. And in the end, in theory, I should have a quarter of the trials as spades, all right? That's the theory. Now it may be off a little bit because it's empirical. It's based upon the experiment. It's not based upon the theory. And it's not always going to work out perfectly. So, first trial, I got a spade. Look at that. So we'll mark it down. Spade. Oh, actually, let's do this. I'm just going to put a tick mark in there under spade. Okay. All right, let's run it again. In fact, we'll do a little shuffle, not a lot in between. And next one, how did I get the same card? That is not a magic trick. Is that the same card? I think I'll have to rewatch that. I think that's the same card. Weird. Okay, got it. I got the shuffle on camera. I'm pretty sure I did that. Okay. Another spade. This is weird. Okay. But not all spades, I'm telling you. That's weird right there, okay? Didn't see that coming. All right, let's try it again. I'm not looking. Okay, club. Got something different. All right, so definitely out of the first 4 tries, I've got 3 out of 4 as my empirical probability. That's kind of interesting. So the first 4, I'm going to have, let's see, it's 3 out of 4 total, right? So it's the observed number of times E occurs, that's 3. And 4 is the total number of occurrences, right? You add them all up. So 3/4 on that one. Definitely not very accurate compared to our theoretical. Let's shuffle again, we'll try it. I don't know why I'm holding the cap in my other hand, there we go. Makes it hard. Another spade. Okay. Yeah, let's just keep running this for a while here. See what happens. Ah, another spade. Why is this all spades? A diamond. Okay, something different. That's nice. They got the king of spade again. What is this? Heart. I'm curious what happens when I get to like 20 of these things. Another spade. Almost think this was weighed heavily on the spades, but I'm pretty sure that it isn't. Club. And heart. And okay, this is, maybe I'll fast forward this on the video. What's that? Spade or diamond? Yeah. I'm just assuming it's spade at this point, right? Diamond. So you can see things are starting to even out a little bit anyway as I go through this more and more. Let's get up to like 20 here total. I got a ways to go, don't I? Another spade. Okay, we're at 15. I got another 5 to go. So let's see. Another king of spade. Weird. All right, I feel like I gotta shuffle more just to make this mixed up. That's a heart. Another heart. Hearts are starting to catch up here. We'll see what happens. Diamond, all right. Another spade. I don't know, am I at 20? I'm probably over 20 by now. I'm not counting these. What do I have? 10, 18, that's 20 right there. Let's stop at 20. So this was for what, 4. Let's go with 20. Let's see. So probability, empirical probability at 20 is I've got 10 over 20, right? Which 10 over 20 reduces down to 1/2. Okay, 3/4 down to 1/2. It's getting closer to 1/4. In fact, if I look at the decimal form of these, right, it's 0.75 down to 0.5. I'm trying to, eventually I probably will get down to 0.25, but it's taking a lot longer than I thought it would because those spades keep coming up. There's a diamond. We'll just do a few more. Club, finally a club. And another diamond. Another spade. There's a club. I really thought it'd be more even as I did this. But in the long run, another spade, look at that. You're not gonna shuffle this time, there's a club. Another club. There's a spade. Right now I'm gonna shuffle a little bit. Another spade. Another spade, my goodness. Club. No red cards recently. Here we go. Let's see. This will be red. Yep. Diamond. Spade. Huh. I really thought this would be no. This is not working, but that's okay. Club. It is kind of working. It's just kind of funny how it's playing out. There's a heart. Club. Spade. Diamond. Diamond. Spade. Spade. Oh. I'm kind of rooting against the spades here. I'm rooting, which is weird. Here's heart. I'm rooting to make this work. Club. All right, I don't know. What do I have here? There's a lot. Let's keep going. I'll get another 10 or so. Here's heart. Club. Spade. Diamond. Another spade. Another spade. Oh, that doesn't count because I just cut that spot. There. Diamond. Heart. Spade. All right. All right. Let's see if we've got this starting to even out or not. What do I have? I don't even know my probability. My empirical probability here is let's see. I've got 5, 10, 15, 23. 23 spades, and how many total? 5, 10, 15, 20, 25, 30, 35, 40, 45, 45, 43, 44, 47, 48, 23 to 48. Okay, I'm just slightly under 50%, just slightly. So it's like 0.49 probably if I were to grab my calculator here and let's check that out. So that's 23 out of 48 is actually about 48%, 47.9, somewhere in there. So close, 48. So yeah, it's just under 50%. 50% would have been 24 out of 48, so I was thinking that. Anyway, if I were to keep doing this, the theory is that as the number of observed occurrences increases, like if I start getting into the hundreds or the thousands, this will start to even out. And the spades will become approximately one quarter of the total distribution, okay, in theory. And so, obviously it's not getting there very fast because it started out very spade heavy, so it's going to take a long time for that to even out, okay? It should eventually. It won't maybe be perfect even over a really long time, but it should in the long run get close. And so there's a theory that we have, it's called the law of large numbers. Which basically states that as the number of observed occurrences increases, gets very, very large or closer to infinity, the empirical probability will approach the theoretical probability. So even though you won't maybe get perfection on the empirical probability right away, you will eventually approach it. It limits to that over a long period of time, okay? So it basically says that as the number of observed occurrences, 2 R's, increases, the empirical probability approaches the theoretical probability. Oops. I think it's time for a new blue marker. There we go. So anyway, as the number of observed occurrences increases, so we go from 4 to 20 to 48 and so on into the hundreds, into the thousands, keep going, cutting the deck, over and over and over again, which you don't want to keep watching them because that took forever just to get 48 of them. This empirical probability, by observing, by the experimentation, will approach the theoretical probability that's done just by calculating the sizes of the sets, okay? Now, these notations are the same, so I might color coordinate this, but what I might say is that as the number of occurrences, approaches infinity, we would say that the empirical probability, color coordinating, that's red, right? The red P of E would approach the theoretical probability, which is P of E. All right, so that's kind of the the notation we may use. The arrow may represent approaching. We're getting closer to, okay? Again, that may take a while now on this one, but eventually it would get pretty close. And you could try this out at home with the flipping of a coin, right? You flip a coin, 5 times, 6 times, 20 times, 150 times. The more you flip the coin, the closer it's going to be to 50-50 on the heads and tails. At the beginning, the first 10, you might be off. It might be 8-2 or something crazy like that, maybe way off. But eventually, over the long haul, for large numbers of trials, it will even out, or it should, in theory, get close to evening out. Okay, so that's the law of large numbers, and then you can kind of see how we can apply and calculate both of these probabilities depending upon the situation.